Hey, chemistry, welcome to another flipped lecture. We're talking today about colligative properties. And this category of chemistry talks about how a solution behaves differently than the solute or the solvent that made it up. So we're going to talk about how a solution behaves differently than the individual components of it. And then we're also going to talk about colloidal suspensions here a little bit, which is something that's like a solution but not really. So without any further ado, let's go ahead and jump into it. So when a solvent dissolves a solute, lots of things change. When you compare a solution to the pure solvent, a solution has a lower vapor pressure. What that means is that less of its molecules go up into the airspace above it. If you have a pure solvent, it evaporates rapidly and builds up a certain amount of pressure above the solution in a sealed container of solvent molecules. Well, as soon as you make that solvent a solution, the solvent hangs out more in the liquid state than it does in the evaporated vapor state. It also has a higher boiling point. The boiling point goes up in the scale, and so again, a solvent will boil at a lower temperature than a solution does. The solution likes to stay in the liquid state longer. It can stick to itself more despite the increased kinetic energy. And it has a lower freezing point. So it remains, again, a liquid longer as you drop the temperature. So the easy way to remember colligative properties is that all three of these properties have to do with the solution remains a liquid longer. It remains a liquid longer versus evaporation. It remains a liquid longer versus boiling, and it remains a liquid longer versus freezing. So all of the liquid aspect of it in its phase changes has gotten bigger. Okay, so that is what we talk about here when we talk about colligative properties. Here's a phase diagram that shows a phase diagram of a pure solvent versus a solution, and you can see that the region of the phase diagram that represents the liquid phase is bigger in all areas. It's bigger in its atmospheric pressure measurement. It's bigger in its temperature measurement on both sides. So the phase diagram shows a enlarged liquid portion. Solutions remain liquid longer. Okay. The more particles or ions that a solute that dissolve, the greater that these changes are. So we use a shorthand of a lowercase letter I to represent how many particles or ions of a solute there are in solution. And then we can talk about the molal constant, which is going to be different for each solution. And we use that to calculate the boiling and freezing point changes of a solution. So if I put salt in water and the boiling point goes up and the freezing point goes down, by how much? And can I do some math to figure that out? The answer is yes. The molal constant is different for each solvent. And then the change in temperature is equal to the dissociation constant. How many particles did this thing break into, and the molal constant for the solvent, K, times the molality. So the equation is delta T equals IKM. Now, something that's strange about your book, and I don't get it, I don't know why, but in your book they don't have the I term. They just say delta T equals Km. Well, the problem with that is that I matters. If you have something that dissolves into two particles like salt, sodium chloride, when you put salt in water, it dissolves into two particles, and so you have to have the molality of the sodium times the molality of the chlorine. If you just say what's the molality and you do the sodium chloride as one unit, you've only got one piece of the picture. You don't have both parts, right? And so the molality of the two have to be combined, and the I term does matter. So as you're looking through your book, you will see delta T equals Km. Not right. That's a typo. That's an error. I don't know why Bob Jones did that. I'm sorry. Stick a little I in there, okay, and then you'll be right. So let's do an example. 30.0 grams of salt is added to 1.00 liters of water. At which temperature will this solution boil? So we can figure out the molality, And we know how many particles salt will dissolve into, sodium ions and chlorine ions, so we can do the math. Okay, here we go. First, we have to get the value of K for water, which is 1.86. You just look that up. You don't have to memorize that. You can't find it anywhere. You just have to look it up on a table. Okay. The molar mass of sodium chloride is 58.44 grams per mole. The density of water is 1 gram per milliliter, or 1 kilogram per liter. So 1.00 liters of water becomes 1.00 kilograms of water. Salt will dissociate into two ions, sodium and chlorine, right? Now this is different than sugar. If I didn't matter, then you'd have salt and sugar both being equally useful to raise boiling points or lower melting points, but that isn't the case. Salt dissociates into two things, okay? So molality is moles of solute per kilogram of solvent. We have 30.00 grams. How many moles is that? There's the molar mass. Do some division. I have 0.51335 moles of solute, okay? We have 1 liter of solvent, which is 1 kilogram. That's handy. So 0.51335 moles per 1 kilogram is 0.51335 molal. So that's the M. I got the term for M. So I is 2, right, because it dissolves into 2 ions. K is 1.86, and the value for M is 0.51335. So I just have to multiply all that together, 2 times 1.86 times 0.51335, and I get 1.90966 degrees Celsius. That's my elevation for the boiling point. Now it's not going to boil at 1.9 degrees. It's going to boil 1.9 degrees higher than it would have boiled before. So I need to first assume that we're at 1 atmosphere of pressure. We are here in Hawaii. People back in Flagstaff where I used to live, this would be a little different. But 1 atmosphere of air pressure normally boils at 100 degrees Celsius. We would expect the solution then to boil at 100 degrees Celsius plus my elevation gives me 101.91 degrees Celsius. Okay, so that is the way that this works. If a concentrated solution is separated from a diluted solution by a semi-permeable membrane, osmosis will occur. This is review, purely review. Biology dealt with this a ton. The more solute that is in a solution, the more the solution wants to have more water to dissolve it. So a solution moves towards a lower solubility or a lower concentration. And as water can move into that to dissolve, it will. And if it has to cross the membrane, we call it osmosis. The tendency of water to move into a more concentrated solution is called osmotic pressure. So if you have two bodies of water, one has more concentrated solute in it than the other does, and you divide them by a semi-permeable membrane, the water will leave the less concentrated area and osmose through the membrane into the more concentrated area to dissolve that. And that tendency of water to move is called osmotic pressure. I think I've told you my story about lobsters. Yeah, I think I told you that. Anyway, if I haven't, asked me, I'll tell you a funny story in class. Okay, so here's an example of osmosis. We have a concentrated solution on the right. We have a pure water solution, so it's not a solution, pure water on the left. Separate them by a selectively permeable membrane. The solute can't move over into the pure water, but the pure water can move through the membrane into the solution. So the water levels will actually change. You'll see the sugar water level rise and the pure water level drop. Okay. In a solution, the dissolved particles do not settle out over time. In a solution, by definition, a solution is dissolved. And so it stays dissolved until you do something strange to it. A colloidal suspension, however, is not a solution. A colloidal suspension are things that are hanging out together but are not dissolved, and they can settle out over time. In a colloidal suspension, in a situation where things will settle, we call the small stuff not a solute, but we call it a dispersed particle because it's scattered out there. Okay, and we don't call the larger component that would be a solvent in a solution. We don't call it a solvent in a colloidal suspension because it's not dissolving anything. We call it the dispersing medium. It's the thing that has stuff dispersed in it. So it's a dispersed particle and a dispersing medium instead of a solute and a solvent, right? Examples of colloidal suspensions. This cafe au lait, when you first make it, you can stir it all together and it's uniform, but give it a second, and the foam will come up to the top, and then the milk will be here, and the espresso will go down here. So this is a settled out cafe au lait or cappuccino, and you can see different layers. And so layers are not a solution. Layers are a suspension. Okay. Smoke in the air. Smoke does not remain dissolved in the air. Smoke does not stay up in the air indefinitely. It eventually falls down, and praise Jesus that it does. Otherwise, there have been plenty of fires in the Earth's history that we would have no more clear skies. So the smoke settles out, and it falls down, and because of that, smoke is a suspension, not a solution. Here we have a demonstration. If you shine a light through a solution, it doesn't scatter the light at all, or if it does, it's very small, because all the particles are dissolved. And so the particles are not big enough to scatter the light. But in a suspension, the particles are not dissolved. And the particles tend to be much larger in a suspension, and they do reflect the light out and scatter the light. And so shine a flashlight through a solution, and it looks just like it's the solution. But you shine a light through a suspension, and you can see the beam of light because it's scattering the light out from larger particles. Okay? Nearly done. Many kinds of colloidal suspensions are very familiar to you. A solid dispersed in a gas is smoke. I just showed you a picture of that. Liquids can be dispersed in a gas, and that's an aerosol, like clouds and things of that nature. Gas can be dispersed in a liquid, and so here we have the liquid as the larger component and gas in it. That's a foam, like shaving cream. There's a whole bunch of them in your book. We're not going to go through all of them here. Just know that there are different kinds of suspensions. Here's a table of some of them. Liquid foam, solid foam. You can have a gas in a solid like styrofoam, right? Liquids in a solid is a gel. Solids in a solid, there's such thing as a solid gel. So lots of different kinds of suspensions, and your book talks about them in detail, and we don't need to go through them all here. Just know that a suspension is different from a solution, and know the different colligative properties and how it works, and that'll be good enough. If you have any questions, put them in the comments field below, and I'll get to you as quickly as I can, or I'll see you in class tomorrow, and we will continue to stumble through this. Jesus loves you, and so do I. God bless you.